and today is the first part of my series in contour integral in physics. So contour integrals appear in complex analysis in math, and it might seem very abstract and inapplicable, but in this series I hope to show you how contour integrals may in fact appear in physics. And the first episode would be topological insulators winding number, and then the second video I plan to do it on the propagator that appears in electrodynamics and quantum field theory. So that will be more exciting, but let's cover this topological insulators one, which is just as exciting also actually. Yeah, so the mathematical statement is to show that this particular integral, where a and b are constants, and integrate with respect to theta, is equals to 0 if a is less than b, or 1 if a is greater than b. So some questions might arise like, how did this kind of discrete behavior start to arise? How did this discrete behavior arise when we have an integral? I mean, seemingly unobvious, but we'll see later in the contour integral that the poles show up in particular manner. And yeah, so a bit of background, how this integral arises is you have the following definition of the winding number from this book. So how do you get from here to there? So essentially this D over here, it describes the SSH model. So this D vector is a function from the brilliant zone, which is the T1 torus. So it's the minus pi to pi, and then you quotient out equivalence relation, where the equivalence relation glues pi and minus pi together onto R2. So yeah, the T1 is just S1. So it's a map from the 1 sphere onto the 2 plane, the R2 plane. So essentially the D vector, we want the winding number here is defined as how many times this D vector winds around the origin. So we label the domain K, and then we maps onto two numbers. So this is D of K, and then as you vary the parameter K, it will trace out a loop, and this winding number measures how many times it winds around this origin. So for a particular model for the SSH model, we have the D vector given by the following, which is b plus a cosine theta and sine theta, a sine theta. So then if you compute this cross product over here, so this cross product essentially takes, so first of all we have the normal, what does this cross product do? You have the normalized vector d tilde, which takes the d vector and then it normalizes it onto the unit sphere. This is d tilde, and then you take the derivative with respect to k, so that tells you how this d vector changes. And then you see that if you have this d vector dot crossed with this d vector, it gives you a vector that is pointing out, right? So and if you do the integral, then essentially it tells you how many times this winds around, because if this d vector goes anti-clockwise and then it goes clockwise, then this derivative would change direction and it will cancel out with the previous loop. So essentially this is, you can take this by definition, and with some manipulation you can show that this leads to v equals to 1 over 2 pi integral from minus pi to pi of the thing that I mentioned just now. So yeah, just note that the theta and k correspond to each other. So essentially that's just the background. So how to compute this integral? We can use complex analysis. So how do we do it? First step is to convert this integral into in terms of z. So you have z, you let z equals to e to I theta. Then you realize that as the theta goes from minus pi to pi, then z essentially goes one round around the complex plane. So your z starts off from here, and then it goes like this. So essentially you have a closed loop integral. So what does this become? So it becomes, so I'll just let this winding number be v. V equals to 1 over 2 pi closed loop integral a square plus ab cosine theta over a square plus b square plus 2ab cosine theta. And then what is d theta? So to calculate, let's calculate cosine theta first. Cosine theta equals to z plus 1 over z, or rather 2 of this. So we can replace this with ab over 2 z plus 1 over z, and then the bottom we replace it with ab z plus 1 over z. And what is dz? dz equals to I e to the power of I theta d theta, which equals to iz d theta. So d theta equals to minus I dz over z. So then you have minus I dz over z. And then this is a contour integral. So you can pull it the factor of I out, and what do you have over here? So you have quite a mess, but let's sort it out. Let's try to make the let's try to make the numerator have be a polynomial in z. So we multiply both the numerator and denominator by z. So you have a squared z plus ab over 2 z plus 1, z squared plus 1, and then the denominator you have ab z squared plus a squared plus b squared z plus ab. Yes, and then you have the 1 over z over here, so it'll be 1 over z. So let's just put this like this, and then dz. So this is now a contour integral over the path c, where c is this anti-clockwise path over here. Okay, so yeah, so before I go further, let me just show you this numerically. So I have a mathematical notebook over here to show how this and I numerically integrate it. So you see that if a is greater than b, then the integral evaluates to 1, and if a is less than b, then the integral evaluates to 0. So that's just some numerical checking of our integral over here. Then let's check it analytically using the following steps that we're doing. So minus I over 2 pi, you see that this is a quadratic, so let's factorize it. So you have the numerator a squared z. Okay, I'll write it. And then you have z, and then you can factorize it. So I won't go through the trouble of writing the quadratic equation, but essentially you can show that this factorizes to become z plus a over b and z plus b over a. Easy. So immediately over here, let's just call this entire function f of z. So what do you notice? We realize the poles of f of z, there are 3 poles, and they are simple poles. So they are 0, minus a over b, and minus b over a. Right? So so from here we have and so what do we see over here? So we see that we have the complex plane. There are some poles. So if this is the 0 pole, then this is our contour C that we're going to integrate over. Then we have, let's say, right, you see that A over B and B over A, only one of them is inside this contour. So for example, if in the case where if A is greater than B, then minus B over A will be inside, right? Because B is smaller than A, and then so this will be minus B over A, the pole minus B over A, and this is the pole minus A over B. So we have three poles. So in this case, if in the case where A is greater than B, then the minus B over A pole is inside, and then this contour integral will simply be the 2 pi I times the residues. So when the two residues at the two poles enclosed, so residue of the 0 pole plus the residue of the minus B over A pole, right? So yeah, that's great. So this is equals to, we can do the multiplication, so that it gives us a residue of the function at 0 and the residue of plus the residue of the function at minus B over A. Okay, so what only remains to do is to compute the residue of this function at the pole 0 and minus B over A. So let's do that. So let me zoom out a bit more. Okay, so I seem to need a bit more space. I can do it on the right over here. So let's do residue of F, since it's at 0. So since it's a simple pole, it is simply Z times F of Z evaluated at Z equals to 0. And so what do you see over here? You see that the numerator is AB over 2 because this term and this term vanishes, and the denominator, this guy is multiplied out, and then the denominator will be over A over B plus A over B times B over A. So this is just simply 1 over 2. So the residue at the 0 pole is 1 over 2. Okay, then how about the residue at the other pole? So I'll just erase this because I need a bit more space. So the residue at the other pole minus B over A is given by Z plus B over A times F of Z evaluated at Z equals to minus B over A. So let's just plug it in. So it's a bit more tedious, but you can still get an answer. So spoiler alert, it's just minus, it's just half. Now I'll just do out all the steps here. Okay, so what do we see here? We see that the first term is b cubed over 2a, and then you have minus ab over 2. Yes, the denominator would be minus b squared a over b minus b over a, and that equals to b cubed over 2a minus the numerator over the denominator is b cubed over a minus ab, and then that will just be 1 over 2. So that is the residue. So we have the two residues, and that will give us 1 over 2 plus 1 over 2, which, surprise, is 1. So remember that this was the case if a is greater than b. So now one could simply repeat the exact same case for I repeat the case for the case where A is less than B, and you'll see that this V equals to 0. So yeah, I will not go through the steps of that because it is pretty much identical, but essentially we have showed that this contour integral depends on the parameters A and B, namely that if A is greater than B, then you get the contour integral is equals to 1. So this is appearance of contour integral in physics, namely it shows up in the winding number, which is sort of a topological invariant, where because the topological invariant under transformations where A is not equal to B. So if you avoid this kind of crossing, then your topological winding number does not change. So this is a cool example of contour integration appearing in physics, and I hope to catch you in the next video where I talk about the propagator. Have a nice day. Bye.